Backend systems rarely fail because of a missing semicolon. The most dangerous crashes happen in the dark, triggered by unhandled domain states, hidden nulls, and memory allocation limits that only reveal themselves under intense production loads. To prevent this, developers traditionally build fortresses of boilerplate. We wrap logic in dynamic proxies, stack defensive guard clauses, and rely on default switch cases that throw exceptions when an unknown state appears at runtime. C#15 addresses this by shifting where the verification happens. It moves risk mitigation out of the runtime environment and directly into the compiler. Catching architectural flaws in the IDE before a single line of intermediate language is compiled provides a more stable foundation for scalable systems. Consider a standard state evaluation and data pipeline written in C#14. On the left, evaluating a state requires nested if statements. Building the output collection involves instantiating a dynamic list and calling .add in a separate step. The process ends with a switch statement that requires a manual exception to catch unhandled types. The C#15 equivalent on the right replaces this with a closed type union, nested property patterns, and a single inline collection expression specifying the exact capacity. C#15 changes how the .NET compiler generates intermediate language for these expressions. Defining domain rules directly in the syntax allows the compiler to enforce logic consistency before the code ever runs. Standard object-oriented programming relies on the open-closed principle. You create a base class like pet and extend it as needed. While this approach is flexible, it's difficult for a compiler to predict. An inheritance tree can have infinite downstream classes added anytime. Because the compiler can't guarantee it knows every possible subclass, it forces a default case in your switch statements to handle the unknown. C#15 introduces type union syntax, a public union named pet composed of exactly 3 types: dog, cat, and bird. This syntax explicitly locks the type definition. It prevents external classes from inheriting from or joining the union, creating a locked container for your data. Restricting the domain model this way allows the compiler to perfectly map the boundaries of your system. Once the domain is closed, the compiler can enforce exact state evaluation through pattern matching. In this switch expression, the compiler proves that every possibility is covered. Since pet can only ever be a dog, cat, or bird, the code is exhaustive without needing a default case. If you update the domain to support a new object, like a shark, you add it directly to the union definition. The compiler instantly flags every existing switch expression interacting with pet. The pattern is no longer exhaustive. The build will fail until you write an explicit path to handle the shark type. Compile time exhaustiveness identifies state handling gaps immediately. It turns what would have been a silent runtime error into a visible development task. To use these structures in high-throughput environments, we must examine how the compiler translates them into physical memory. While some languages use simple memory tags, C#15 generates a structural wrapper, a partial record struct that implements an IUnion interface. Inside this struct is a single read-only object property that stores your data. This design allows almost any type to be stored as an object reference, but it introduces a performance trade-off for value types. When you assign a value type, such as a record struct cat, to this union, it is boxed. Boxing moves the value type to the heap, where it must be managed by the garbage collector. This adds a small amount of compute overhead. Future updates are expected to allow manual memory layouts for value type-only unions to avoid this overhead. Understanding this memory layout helps architects avoid unexpected garbage collection lag in latency-sensitive microservices. Another major source of runtime friction: dynamic memory allocation in collections. When a dynamic array, like a list, exceeds its capacity, it must allocate a new, larger block of memory and copy all existing data over to the new location. In high-scale processing, dynamic reallocation causes performance spikes. C#15 fixes this with collection expression arguments. Adding a capacity directly passes parameters in line. The compiler reads the capacity first, allocating a perfectly sized memory block before adding any data. This process circumvents dynamic resizing, allowing data to stream in without allocation penalties. This same syntax can be used for other constructor needs, such as passing a case-insensitive string comparer to a hash set constructor. Collection expression arguments provide precise control over memory while maintaining a clean, readable syntax. Type unions and inline collection arguments represent a broader architectural movement in .NET, moving verification from runtime to compile time. Looking at our C#15 implementation again, we see two distinct advantages. The type union provides logic verification that ensures every possible state is accounted for. The inline constructor arguments provide memory efficiency by eliminating the need for dynamic resizing. The trajectory of the C# language is to shift complexity and risk away from the runtime execution path. Automating state verification and memory constraints prevents common runtime failures like unhandled case exceptions and dynamic resizing overhead. Backend systems scale more effectively when their operational intent is strictly declared. By adopting C#15, architects can build systems with harder logic boundaries and highly predictable memory footprints.
Thanks for watching this video. If you enjoyed this video, please hit the like button and the bell notification icon.